Picture this. It's March 15th, 1943, and Lieutenant Commander William Murphy stands on the deck of the USS Hornet watching enemy aircraft dive toward his task force through the Pacific dawn. The ship's 5-inch guns thunder around him, sending shell after shell screaming into the sky. But here's the thing that's eating at Murphy's gut. Every single one of those shells is missing. The Japanese planes weave through the barrage like ghosts, untouchable, deadly, closing in for the kill. Murphy has watched this same nightmare play out dozens of times across the Pacific. American gunners firing thousands of rounds at enemy aircraft, hitting almost nothing, watching helplessly as Japanese bombers slip through their defenses to savage American ships and crews. The mathematics are brutal and undeniable. American anti-aircraft guns hit their targets less than 2% of the time. 2%. That means for every 100 shells fired at enemy planes, 98 explode uselessly in empty air, while the other 2 might, if luck favors the gunners, actually damage something. But what Lieutenant Commander Murphy doesn't know, what none of the sailors desperately manning those guns can possibly imagine, is that 3,000 miles away, in a secret laboratory buried beneath the streets of Washington, D.C., American scientists are about to solve this problem in the most ingenious way imaginable. They're going to put radio tubes inside artillery shells. Not just any radio tubes, but miniaturized electronic brains that can think faster than human reflexes, calculate trajectories in milliseconds, and turn every shell into a precision-guided weapon of devastating accuracy. The story of how America revolutionized warfare by shrinking an entire radio receiver into something small enough to fit inside an artillery shell begins not with military planners or weapons designers, but with a soft-spoken physicist named Merle Tuve working in the basement of the Carnegie Institution. Tuve doesn't look like someone who's about to change the course of World War II forever. He's thin, scholarly, the kind of man you'd expect to find teaching college physics rather than designing weapons of war. But behind those wire-rimmed glasses burns an intellect that grasps something no one else has considered. What if artillery shells could think? The problem American forces face in 1943 is fundamentally simple to understand, but impossibly difficult to solve. When a gunner fires at an enemy aircraft, he's not shooting at where the plane is. He's shooting at where he thinks the plane will be several seconds in the future when his shell reaches that altitude. It's like trying to hit a moving target while blindfolded, riding a roller coaster in the middle of an earthquake. The human brain simply cannot process the variables fast enough. Wind speed, air density, aircraft velocity, shell trajectory, fuse timing. By the time a gunner calculates where to aim, the target has moved somewhere completely different. Traditional artillery shells use mechanical time fuses. A gunner estimates how long the shell will take to reach the target area, sets a timer, and hopes the explosion happens at the right moment. But mechanical timers are crude instruments, accurate to maybe half a second at best. Against aircraft moving at 300 miles per hour, half a second means the difference between a direct hit and a complete miss. The Japanese understand this limitation perfectly, which is why their pilots fly with such apparent impunity through American anti-aircraft fire. Dr. Tuve realizes that the solution isn't bigger guns or more ammunition. The solution is intelligence. Not human intelligence, which is too slow, but electronic intelligence that can react faster than any human ever could. He envisions artillery shells equipped with tiny radio transmitters that broadcast signals ahead of the shell's flight path. When those radio waves bounce off an enemy aircraft and return to the shell, the electronic brain inside calculates the distance instantly and detonates the explosive at exactly the right moment to cause maximum damage. The concept is brilliant in its simplicity, but the engineering challenges are staggering. In 1943, the smallest radio receivers weigh several pounds and require multiple vacuum tubes, complex wiring, and delicate components that would shatter under the tremendous forces generated when an artillery shell fires. The acceleration inside a 5-inch gun barrel reaches 20,000 times the force of gravity. It's like trying to build a wristwatch that continues telling time after being shot out of a cannon. But Tuve and his team at the National Defense Research Committee understand that this impossible challenge represents the difference between American victory and defeat in the Pacific. Japanese aircraft are sinking American ships faster than American shipyards can replace them. Something has to change, and it has to change immediately. The scientists begin working 18-hour days, 7 days a week, sleeping on cots in their laboratory, eating sandwiches at their workbenches, driven by the knowledge that every day they delay costs American lives. The breakthrough comes from an unexpected source. Bell Telephone Laboratories, the research arm of the American telephone system, has been experimenting with miniaturized vacuum tubes for civilian applications. These tiny electronic components, originally designed to fit inside home radios, prove just rugged enough to survive the brutal acceleration of artillery fire. But surviving the launch is only the beginning. The radio receiver must also function flawlessly during the shell's flight, transmitting and receiving signals while spinning at thousands of revolutions per minute, buffeted by wind forces that would tear apart conventional electronics. The team develops what they codename the Variable Time Fuse, or VT fuse for short. The name is deliberately misleading, designed to confuse enemy intelligence. There's nothing variable about the timing. Instead, the fuse uses a miniature radio transmitter that broadcasts continuously during the shell's flight. When the radio waves encounter a target and bounce back to the shell, a receiver circuit measures the signal strength and calculates the distance to the target. When that distance falls below a predetermined threshold, typically about 70 feet, the fuse detonates the shell's explosive payload. The engineering elegance of this system cannot be overstated. Unlike mechanical time fuses that depend on human estimation and mechanical precision, the VT fuse adapts automatically to actual battlefield conditions. If the target aircraft suddenly changes course, the fuse adjusts its detonation timing instantly. If wind conditions alter the shell's trajectory, the fuse compensates without human intervention. Each shell becomes an individual hunter, seeking its prey with electronic senses far more acute than human perception. Testing begins at the Dahlgren Naval Proving Ground in Virginia, where prototypes are fired at remote-controlled target drones. The results exceed everyone's expectations. Shells equipped with VT fuses achieve hit rates approaching 40%, compared to the traditional 2% accuracy of mechanical time fuses. It's a 20-fold improvement in battlefield effectiveness, transforming anti-aircraft artillery from a psychological weapon into a genuine threat to enemy aviation. But the real test comes not in Virginia Proving Grounds, but in the blood-soaked waters of the Pacific, where American sailors face Japanese aircraft in daily combat. The first operational VT fuses are loaded aboard ships of the U.S. Pacific Fleet in late 1943, accompanied by strict security protocols. Gunners are forbidden from using the new ammunition over land, where unexploded shells might be recovered by enemy forces and reverse-engineered. The technology is so revolutionary, so potentially war-changing, that American commanders treat each VT shell like a piece of classified information that must never fall into enemy hands. The stage is set for one of the most dramatic technological surprises in military history. American ships carrying weapons that enemy pilots have never encountered, guided by electronic brains that think faster than human reflexes, are about to meet Japanese aircraft in battles that will determine the fate of nations. What happens next will prove that sometimes the difference between victory and defeat comes not from courage or numbers, but from the brilliance of scientists working in basement laboratories, solving impossible problems with solutions that seem like science fiction. The first real test comes on January 11, 1944, during what becomes known as the Battle of Anzio. American destroyers equipped with the secret VT Fuzes face German Junkers 88 bombers attempting to destroy Allied landing craft in the Mediterranean. Gunner's mate first class. Tony Rodriguez mans a 5-inch gun aboard the USS Plunkett, loading shells that look identical to conventional ammunition, except for small antenna wires protruding from their nose cones. Rodriguez has no idea what makes these shells different. The Navy has told him only that they're experimental rounds with special timing mechanisms. But when the first wave of German bombers appears on the horizon, diving toward the vulnerable transport ships, Rodriguez begins firing with ammunition that will change warfare forever. The first VT shell explodes 73 feet from a Junkers 88, close enough that the blast wave tears off the bomber's port wing. The aircraft cartwheels into the Mediterranean in a ball of flame. Rodriguez stares in disbelief. He's been firing anti-aircraft guns for 18 months, watching thousands of shells explode harmlessly in empty sky. Now suddenly his ammunition seems to possess an uncanny ability to detonate at exactly the right moment, exactly the right distance from enemy aircraft. Within minutes, 3 more German bombers fall to his gun, their twisted wreckage scattered across the Italian coastline. Across the fleet, the same impossible accuracy repeats itself. Gunners who struggled for months to hit anything suddenly find themselves destroying enemy aircraft with devastating efficiency. The German pilots, veterans of campaigns across Europe, have never encountered defensive fire like this. Their standard evasive maneuvers, perfected against conventional anti-aircraft guns, prove useless against shells that seem to anticipate their every move. But the real revelation comes 3 weeks later in the Pacific, where Admiral Mark Mitcher's Task Force 58 faces the largest Japanese air attack since Pearl Harbor. 250 Japanese aircraft, the cream of the Imperial Navy's remaining aviation forces, converge on the American fleet in what they believe will be a decisive blow against American naval power. They have no conception of what awaits them. Commander James Mitchell stands in the Combat Information Center aboard the USS Yorktown, watching radar screens display the incoming raid as a solid mass of enemy contacts. Traditional doctrine would call for launching every available fighter aircraft and hoping they can intercept enough bombers to prevent catastrophic damage to the fleet. But Mitchell has something better than hope. He has 5-inch guns loaded with ammunition that thinks faster than enemy pilots can react. The Japanese formation approaches at 15,000 feet, their pilots confident in their ability to penetrate American defenses. They've done it dozens of times before, weaving through curtains of anti-aircraft fire that seemed more like fireworks displays than serious threats. But as they close within range of the American ships, something unprecedented happens. The sky around them begins exploding with surgical precision. Lieutenant Saburo Sakai, one of Japan's most experienced fighter pilots, watches in growing horror as American shells detonate mere feet from aircraft throughout his formation. This isn't the random scattered fire he's encountered in previous battles. These explosions seem targeted, personal, as if each shell possesses its own intelligence and malevolent intent. Within minutes, 63 Japanese aircraft have been destroyed by anti-aircraft fire alone, a casualty rate that defies every tactical manual in the Imperial Navy. The electronic brains inside the VT fuses are performing exactly as Dr. Tuve envisioned. Each shell broadcasts its radio signal thousands of times per second, measuring the distance to nearby aircraft with mathematical precision. When a Japanese bomber enters the 70-foot kill zone, the fuse triggers instantaneously, creating a sphere of deadly shrapnel that no aircraft can survive. The system is so effective that Japanese pilots begin reporting attacks by a new type of American weapon they cannot understand or counter. Back in his Washington laboratory, Dr. Tuve receives battle reports that read like science fiction. American ships reporting hit rates of 35 to 40% against enemy aircraft. Japanese formations being decimated before they can reach their targets. The 2% accuracy that plagued American anti-aircraft guns for the first 2 years of the war has been transformed into a killing efficiency that borders on the supernatural. But the true genius of the VT fuse reveals itself in its adaptability. Unlike mechanical time fuses that require gunners to estimate target distance and flight time, the electronic fuse adjusts automatically to battlefield conditions. When Japanese pilots attempt evasive maneuvers, climbing or diving to escape the killing zone, the VT shell follows them electronically, detonating whenever the radio signal indicates optimal range. When wind conditions alter shell trajectories, the fuse compensates without human intervention. Each round becomes an autonomous hunter, seeking enemy aircraft with senses far superior to human perception. The psychological impact on Japanese aviation proves as devastating as the physical destruction. Pilots who survive encounters with VT-fused shells return to their carriers with reports of American ammunition that seems to possess supernatural intelligence. The technical superiority they've enjoyed since Pearl Harbor suddenly evaporates, replaced by a growing realization that American industry has produced something beyond their comprehension or ability to counter. Emperor Hirohito's naval staff begins receiving increasingly desperate reports from fleet commanders. American anti-aircraft fire has become so accurate that Japanese bombing missions are suffering 70% casualty rates. Experienced pilots, irreplaceable after 3 years of combat, are being shot down faster than training programs can produce replacements. The mathematical reality becomes undeniable. Japan cannot sustain losses at this rate while American defensive capabilities continue improving. Admiral Chester Nimitz, reviewing casualty reports from recent Pacific battles, realizes he's witnessing a fundamental shift in naval warfare. For the first time since the war began, American ships can defend themselves effectively against air attack. The desperate defensive battles of 1942 and early 1943, where survival depended on fighter aircraft and luck, have been replaced by coordinated defensive systems that turn approaching enemy aircraft into statistical probabilities rather than mortal threats. The secret remains so closely guarded that even American gunners don't understand why their accuracy has improved so dramatically. They're told only that new ammunition requires special handling procedures and must never be fired over land where unexploded shells might be recovered by enemy forces. The true nature of the VT fuse is classified at the highest levels of government, known only to a handful of scientists, military commanders, and production workers who sign oaths of secrecy that carry prison sentences for violation. The production challenges facing American industry in late 1944 would have seemed impossible just 2 years earlier. Each VT fuse required 17 precision-manufactured vacuum tubes, smaller than a human thumb, but capable of withstanding forces that would crush conventional electronics. The tubes had to be assembled by hand, tested individually, then carefully installed inside artillery shells using techniques that didn't exist when the war began. Every component had to meet tolerances measured in thousandths of an inch, because a single manufacturing defect could render an entire shell useless, or worse, cause it to detonate prematurely and kill American gunners. The Bell Telephone Laboratories facility in Murray Hill, New Jersey, becomes the epicenter of this industrial revolution. Engineers who once designed telephone switching equipment now spend their days perfecting miniature radio circuits that must function flawlessly while spinning at 12,000 revolutions per minute. The assembly process reads like a medical procedure. Technicians wearing white coats and surgical gloves position vacuum tubes inside specially designed shock mounts, then seal the entire assembly inside waterproof casings that protect the electronics from moisture, temperature extremes, and the tremendous stresses of artillery fire. But the most challenging aspect of VT fuse production isn't technical, it's human. The workers assembling these devices have no idea what they're building. Security protocols prohibit discussing the fuse's purpose or destination. Women who spend 10 hours a day soldering tiny electronic components believe they're manufacturing radio equipment for civilian applications. Men who machine the precision metal housings think they're producing parts for aircraft instruments. The compartmentalization is so complete that even supervisors understand only their specific portion of the production process. Mary Catherine Sullivan, a 23-year-old electrical engineering graduate from Boston University, finds herself assigned to a windowless factory floor in suburban Maryland, testing circuits whose function remains mysterious. Her job involves connecting each completed fuse to diagnostic equipment that measures radio frequency output, signal strength, and timing precision. Sullivan doesn't know that the devices she's testing will soon be killing Japanese pilots over the Philippine Sea. She knows only that her measurements must fall within extremely narrow parameters, and that rejected units are immediately destroyed rather than repaired. The secrecy surrounding VT fuse production creates an atmosphere of barely controlled paranoia. FBI agents conduct regular security inspections at manufacturing facilities, interviewing workers about their conversations, monitoring their personal relationships, investigating anyone who asks too many questions about their assignments. The penalty for security violations is immediate termination and possible prosecution for treason. Workers develop an unspoken understanding that ignorance is not just bliss, it's survival. Meanwhile, in the Pacific, American fleet commanders are discovering that their new ammunition creates tactical possibilities that didn't exist 6 months earlier. Admiral William Halsey, commanding the Third Fleet during the Battle of Leyte Gulf, realizes that ships equipped with VT fuses can operate independently without massive fighter aircraft protection. The electronic shells have transformed individual vessels into autonomous defensive platforms capable of engaging multiple targets simultaneously with unprecedented accuracy. The mathematical transformation is staggering. A single American destroyer, previously vulnerable to coordinated air attack, can now engage 8 to 10 enemy aircraft simultaneously with reasonable expectation of destroying at least half of them. Cruisers with their larger gun batteries become virtually impregnable to conventional bombing attacks. Even battleships traditionally considered obsolete in an age of aircraft carriers regain tactical relevance as floating anti-aircraft platforms capable of creating protective umbrellas over entire task forces. Lieutenant Commander Robert Sinclair, gunnery officer aboard the USS Washington, watches his 5-inch batteries engage a formation of Japanese dive bombers approaching from the northwest. Traditional doctrine would have required his gunners to concentrate fire on the leading aircraft, hoping to disrupt the attack formation. Instead, Sinclair orders his batteries to engage multiple targets simultaneously, confident that the VT fuses will compensate for human limitations in target tracking and range estimation. The results exceed his most optimistic projections. 8 Japanese aircraft enter his gun's engagement zone. Within 90 seconds, 6 have been destroyed by shells that seem to explode with supernatural timing. The surviving bombers, their formation shattered and their attack coordination destroyed, jettison their bombs harmlessly into the ocean and retreat toward their carriers. Sinclair's guns have achieved a 75% kill rate against aircraft that would have devastated his ship just months earlier. But the true strategic impact of VT technology becomes apparent during the Great Marianas Turkey Shoot of June 1944, when Admiral Raymond Spruance's Task Force 58 faces 450 Japanese aircraft in what becomes the largest carrier battle in naval history. Japanese commanders planning their attack calculate that even with expected losses to American fighters, enough bombers will survive to cripple the American fleet and potentially alter the Pacific War's trajectory. They have no conception of what awaits them. American ships bristling with VT-equipped guns create interlocking fields of defensive fire that turn the sky itself into a killing ground. Japanese pilots, veterans of campaigns across the Pacific, find themselves flying through curtains of explosions that seem to anticipate their every maneuver. The electronic fuses, calculating distances thousands of times per second, create a defensive network that human reflexes cannot penetrate or escape. Captain Joseph Clark, commanding the USS Hornet, stands on his bridge watching the most one-sided aerial battle in naval history unfold around his task force. Japanese aircraft diving toward his ships are systematically destroyed by anti-aircraft fire that achieves hit rates approaching 50%. The mathematical precision is almost beautiful in its lethality. Shells exploding at exactly the right altitude, exactly the right distance from their targets, creating spheres of destruction that no aircraft can survive. And so, from the basement laboratories of Washington to the blood-soaked waters of the Pacific, American ingenuity transformed the mathematics of aerial warfare forever. Dr. Tuve's impossible dream of thinking artillery shells became Japan's nightmare, turning 2% accuracy into 50% devastation. The radio tubes that once brought music into American homes now brought death to enemy aircraft with electronic precision that human reflexes could never match.